Hello, welcome back. We have been discussing the first unit of applied physics, that is quantum mechanics. In this video, we'll discuss the origin of energy bands in solids. Suppose you have an atom and one of its energy levels is like this. For an atomic system, the energy levels are very sharp and they are discrete in nature, which means if you draw the energy spectrum of an atom, you might get something similar to this. You'll get sharp energy levels, say E1, E2, E3, so on and so forth. Which means if you have a single atom, the energy levels are quite sharp and well-defined energy levels. These energy levels are nothing but the electronic states in the atom, and this is called the energy spectrum. Suppose there are two identical atoms brought close to one another, then wave function of the outermost electrons is slightly disturbed. As a consequence, instead of getting one energy level for E1, we are likely to get one more energy level corresponding to the other atom, that is E2. In fact, for these two atoms, there is only one energy level, but there will be a splitting of the energy levels because of the presence of the other atom. And similarly, if you have four atoms like that, then you see that the energy level E1 here initially, this is undergoing a splitting into four different energy levels that are closely spaced. And if you have a very large number of atoms, let's say n atoms in a solid, maybe like this, then the energy levels are splitted into n different energy levels, and these energy levels, they fall into a band of energy levels, and this band is called as energy band. And the splitting of the energy levels can also be attributed to the thermal agitations of the atoms. When the temperature is above the 0 Kelvin, the atoms attached to the lattice, they will be vibrating about their mean position, which is the lattice point. Since they are also vibrating, they will have its influence on the neighboring atoms and their energy levels. As a consequence, we will observe a band of energy levels corresponding to each of the atomic levels in the atomic spectrum. And these band of energy levels thickness depends very much on how the electronic wave functions are overlapping one atom to the other atom, or between the atoms, how the electronic wave function is going to overlap. That will determine the thickness of the bands. If you have a large number of atoms like this, we might get a band of energy levels like this. An energy band is nothing but the energy levels that are closely spaced to one another. The difference between the energy levels could be less than 0.01 electron volt. So the energy levels difference is very small and they form into a group, and the group of energy levels is called as energy bands. Now here we have atomic spacing along the x direction, the energy along the y direction. If the atomic spacing is large, you have a gas where the electronic states are discrete in nature. For instance, you might have seen sodium vapor lamps on the streets. So these sodium vapor lamps are made up of sodium vapor. Electronic transitions in the sodium vapor are responsible for the emission of light in this color. This means we have a discrete energy levels. Between those discrete energy levels, there are transitions that are giving rise to this kind of an yellow color. The yellow color in sodium is resultant of a transition from a higher energy level to a lower energy level. You do not have energy bands because a vapor state of a metal is a gas form. So we are getting a discrete energy levels, and a transition between two discrete energy levels is going to be a given color in the visible spectrum. So this kind of a thing happens only when the separation between the atoms is large, or the atomic spacing is large, then you have a gas. When the atomic spacing becomes smaller, you will have a solid. For instance, you have lead. For lead, you see the bands are overlapping. Reason being, the lead is a metal. And similarly, tin. For tin also the bands are overlapping. But when it comes to germanium, silicon and carbon, the bands are separated by electron volts. Here it is couple of electron volts. In semiconductors, the gap between the energy bands will be about an electron volt, whereas in the carbon it is about 5 electron volts, and in dielectrics it can be about 10 or even more electron volts. In our discussion we are mainly concerned about the bands that are formed by the outermost electronic states and the next electronic states. The outermost electronic states of an atom in a solid are called as the conduction band, and the next energy level, that is called as the valence band. Other electronic bands, that are the inner bands, they do not contribute much to the electrical or physical properties of the solid. So these two bands of energy levels are responsible for various physical properties of the solids, such as electrical conductivity, thermal conductivity, and many other physical properties. Between the energy bands, we have what is known as the forbidden energy gap. Between bands like this, you will have a forbidden gap. So these energy levels are forbidden as far as the electrons are concerned. And at 0 Kelvin, the conduction band will be empty, and all the electrons, they will be confining to the valence band. There are no free electrons. And when the temperature is above the 0 Kelvin, slowly the electrons will be excited to the higher energy levels of valence band. They will be released into the solid. As a consequence, we will have the free electrons in the solid. Those free electrons, they contribute to the conduction. Hence, it is called as the conduction band. So at 0 Kelvin, we do not have a conduction band, and at any other temperature we start having the conduction band. In this video, we have seen the atomic energy levels, how the atomic energy levels will be splitting as two or more number of atoms are brought close to one another. If you have one atom, a similar atom is brought close to the first atom, then you see that the energy level E1 is splitting into E1 and E2. We will have two energy levels that are closely spaced, and when you have 4 atoms, then the energy level is splitted into 4, E1, E2, E3 and E4. And similarly, if you have n number of atoms, then these n number of atoms will have contribution to the splitting of energy levels into n different closely spaced energy levels, which otherwise looks like a continuum of energy levels leading into the formation of energy bands. We call such group of energy levels that are separated by very small amount of energy as energy band. And these energy bands are resulting because of the wave function of the outermost electrons is shared by the other atoms. As a consequence, the electronic states are splitted. We have seen how the atomic spectrum will contribute to a single discrete energy levels using the sodium vapor lamp. Using this diagram, we have seen in the case of gases, we will have discrete energy levels, and in the case of metals, the energy levels are continuous. And in the case of semiconductors, we have seen that there are two bands. The uppermost band is called the conduction band, and the next to that is called the valence band. There are other bands are also possible, but these two bands are important to understand the physical properties of the solids, namely as electrical conductivity, thermal conductivity, and between the allowed energy bands will have the forbidden energy gap. At 0 Kelvin, the conduction band disappears because there are no thermal agitations and there are no thermal vibrations. As a consequence, there are no free electrons present in the solid. When there are no free electrons present in the solid, then all the conduction band energy levels, they will be empty. Hence we say that the conduction band will be empty at 0 Kelvin. Only at temperatures above the 0 Kelvin will have the band structure for the energy levels. Thank you.